Hello, everyone, and welcome to the VaNTAGe seminar. Today, we're continuing our series on rational points on higher genus curves and the Chabauty method. And we're very happy to have Alex Betts, who's going to be talking about bounding rational points using non-abelian Chabauty. And Alex, is it all right for us to record this talk?
It is, yes.
Oh, great. And feel free, everyone, to ask questions during the talk. Alex, please go ahead.
Thank you. So it's a great pleasure to be with you all virtually today, and to I'd like to thank Rachel and Drew for having extended me the invitation to talk about some ideas that I guess I was thinking about a couple of years ago now. But hopefully this will present a nice complement to what Jen was talking about 2 weeks ago. So somehow where Jen gave a very nice overview of all the sort of things you can do computationally using quadratic Chabauty and some of the real successes we've had in actually computing rational points on actual curves using it. And I guess what I'm going to be talking about today is somehow a more theoretical side of non-abelian Chabauty and its applications to bounding the number of rational points on curves. So I'm going to begin by just with the effective Mordell conjecture. So, since the work of Felting's, we obviously know that the set of rational points on a curve of genus at least 2 is always finite. But this is not really believed to be the end of the story, and there's many more things that we would like to be able to say about rational points on curves, which people often refer to as effective Mordell or effective Felting's. And really, there are two kind of different things people mean when they use the word effective here. One thing one might mean by effective Mordell is somehow an algorithmic version of the Mordell conjecture. So if I give you equations for a curve of genus at least 2, say over the rational numbers, is there an algorithm which provably outputs the set of rational points? And there are various different flavors one could think about this problem for. So one could try and come up with a theoretical algorithm, which, if you had a galaxy-sized Turing machine, would eventually output the answer. But you could also, try and work out if you have a practical algorithm which will, in practice, work for this. And this is something where Chabauty has a lot of successes. And I guess I also mentioned here on the slide, one way you could compute the set of rational points would be if you could prove a bound on the height of rational points, then you just search up to that height bound. And that's one thing that people also mean sometimes when they talk about effective Chabauty, or sorry, effective Mordell. But today I want to focus on a different effective aspect of Mordell, which is, if I have a curve of genus at least 2, can I say anything about the number of rational points? So can I produce an upper bound on the size of the set of rational points? And I'm deliberately phrasing this question in a slightly vague manner. So the gold standard, the thing we would all really like to be able to achieve, is to give a bound on the number of rational points on a curve, which depends only on the genus. And this would resolve the famous uniformity conjecture. But it's still very interesting to see what kinds of bounds one can obtain, even if they don't depend on just the genus. Maybe they depend on other things as well. And so in terms of what's known with regards to this second problem, I think there are really two different, I'm going to be talking about two different sources of bounds on the number of rational points. The first one is not really going to be my main focus today, but it would certainly be remiss of me not to mention a whole suite of ideas coming from Diophantine approximation and really motivated by Voiter's proof of the Mordell conjecture. And these really give us the best available results on bounding numbers of rational points. So first of all, the best known bound on the number of rational points is proved by Dimitrov, Gao, and Haviger a couple of years ago. And what they showed is that you can bound the number of rational points on a curve by some function which depends on just the genus and the Mordell-Weil rank of the Jacobian of X. There's also some implicit dependence on the base field, but my base field is always Q. And much earlier than this, for a very particular equation, one of the simplest kinds of Diophantine equations, called the S-unit equation. This was studied by Evertse, who also used Diophantine approximation techniques to give you an upper bound on the number of solutions to that equation. So the S-unit equation is someone gives you a finite set of primes, this S, and you're trying to solve the equation A plus B equals C, where you take co-prime integers A, B, and C, and the only prime factors you're allowed to see in them are those ones in S. And Evertse gives this lovely exponential bound on the number of solutions to this equation in terms of just in terms of the size of S. So the results I'm going to be talking about today don't actually prove quite as strong theorems as you can prove it using Diophantine approximation, but they come from an entirely separate place, namely non-abelian Chabauty. So this is again a sort of chain of ideas which begins quite a while ago with so Chabauty's proof of some cases of the Mordell conjecture. So back in 1941, Chabauty proved that if this Mordell V rank of the Jacobian is strictly less than the genus, then you have finitely many rational points. And it was realized some 44 years later by Robert Coleman that actually you can make Chabauty's method effective and use it to actually say something about the set of rational points. So what Coleman proved is in this same setup, where the rank is less than the genus, if you take a prime of good reduction, which is at least 2g, then the number of rational points in your curve is bounded above by the number of FP points plus 2g minus 2. So this is actually this is a remarkable bound. Like when it applies, it gives you a very usually a very small bound on the number of rational points. And this bound here is, I guess this is not really a uniform bound in the sense that it depends on the number of FP points, where P is the, say, smallest prime of good reduction. But some more recent work of Katz, Rabinoff, and Zurich Brown show that if you're prepared to strengthen your rank and genus inequality, you can in fact get a uniform bound which doesn't depend on P. And so, yeah, these are again effective effective Mordell results, but they're coming from an entirely different source. And then this has all been in the context of like Chabauty's original method, which I'm referring to here as abelian Chabauty, because this was generalized in the early 2000s by Mignon to the theory of non-abelian Chabauty. And it's possible to use non-abelian Chabauty also to access these kinds of results. So I think the first result in this direction was proved by Jen and Netan, and this was in the setting of what's called quadratic Chabauty. And so I'll actually explain some aspects of this proof later. But yeah, if you're outside the original Chabauty setup, so you have the rank actually equals the genus, but if this quantity called rho, which is the rational Picard number of the Jacobian, if that number is at least 2, then you get a bound on the number of rational points on X of this form here. So it depends on the genus and this prime of good reduction that you chose. So I think the overall aim of what I'm talking about today is to firstly to kind of give you an idea of where these sorts of results come from. Like, how does one use non-abelian Chabauty to bound numbers of rational points? What things does one need to do? And also to just tell you some of these, how to extend these results beyond, I guess, beyond the case where the rank is equal to the genus and beyond abelian and beyond quadratic Chabauty. And in order to do that, I think the first thing I'm going to do is just describe in very broad terms what's going on with this non-abelian Chabauty method. So I think the sort of motivation here really, well, one way to motivate it comes actually from a sort of topological perspective on these sorts of problems. So we're looking at some curve over the rationals of genus at least 2, and we're going to assume that we have some rational base point on our curve, so a point we're going to use to set up the method. And in this case, you can define what's called the QP pro-unipotent et al. Fundamental group of X based at B. This is this object denoted here by pi1 QP of XQ bar based at B. And it doesn't really matter what this is, but you should think this is some kind of group, and it's sort of analogous to the thing you have in topology, which is the fundamental group of a surface based at a base point here. So I sort of got a little cartoon at the bottom of the screen where you have this, your base point B, and elements of this pro-unipotent et al. Fundamental group you should think of as some kind of like loop starting and ending at B. And you can actually do slightly better than this. If you have a second rational point, you can also think about the this pro-unipotent torsor of paths, which is again, it's some defined in some very abstract way, but you should think of it as analogous to the set of homotopy classes of paths from B to X inside your surface. And one of the kind of features of this theory is because everything is, because we're working in the world of arithmetic geometry, these fundamental groups and these path torsors, they don't just exist on their own as like an abstract group and an abstract set, but they actually come with actions of the Galois group of the rational numbers. So if you have a loop based at B or a path from B to X, and you apply different elements of the Galois group, you end up with a sequence of different loops and paths. So somehow the idea is that non-abelian Chabauty is all about leveraging this Galois action to say something about rational points. And we sort of get to this through some kind of obstruction style argument. So I mentioned that if you have a rational point X, then the paths from B to X carries an action of the global Galois group of Q. There's also a local version of this. If I have a p-adic point on my curve, then I get an action of the local Galois group, the decomposition group at P, on the paths from B to X. And so in some sense, non-abelian Chabauty is trying to answer the question, when does this local Galois action look like the restriction of a global Galois action? And obviously, if this p-adic point X happens to be rational, then this is the restriction of a global Galois action. And so by trying to answer this question of when does the local Galois action have a restriction of a global one, you might be able to say something about where the rational points lie inside the p-adic points. So the way we actually make this precise and mathematical is by means of a certain commuting square, which I'm going to call the non-abelian Chabauty square. So here on the top row, I've just got the set of rational points embedding inside the set of QP points, and this is somehow what we're wanting to study. And we're going to study it using using this fundamental group. So I think I forgot to write this down on the slide, but we're going to choose some quotient of the fundamental group, which I'm going to call capital U, that will make everything finite dimensional here. And so then on the left-hand side of this square, in the lower left corner, I have this object here, which is called the global Selmer scheme. And what this is, roughly speaking, this is a moduli space of torsors under this group U with a compatible action of the global Galois group. And if we think back to our topological intuition of thinking about paths from B to a point X, well, that collection of paths, it has this Galois action I described. And you can also pre-compose paths with loops based at B. And so that collection of paths is a torsor under the fundamental group. So this lower left-hand corner is somehow things which kind of look like the sets of paths between two rational points in a curve with its global Galois action. And indeed, this map J here, the global non-abelian Cohen map, this is exactly just taking a rational point X to the torso of paths. And then on the right-hand side, you have a exactly parallel story. So I think I should assume at some point that this prime P is of good reduction. And then this lower right-hand side, this is like a moduli space of torsos under this group U with a local Galois action. And again, this local Cohen map JP takes a p-adic point to the paths from B to X. And this and then the final part of this diagram is this localization map in the middle. And this is just, if I have a torso under the group U with an action of the global Galois group, I'm just going to forget the global Galois action and only remember the local Galois action. So the kind of key input here, which makes the whole theory work, is something which Mignon proved, which is that these two moduli spaces, these are actually affine QP schemes, which are, if you choose U to be finite dimensional, they're actually affine of finite type. And this map between them is actually an algebraic map. It's a morphism of schemes. And the way you can leverage this to say anything about rational points, well, because these local and global Selma schemes are schemes, one can talk about their dimension. And sort of the big, I guess the theorem which allows you to access finiteness via these methods is that if the dimension of the global Selma scheme is strictly less than the dimension of the local Selma scheme, then you actually know that the set of rational points is finite. And to kind of indicate with reference to this square how this goes, the idea is this localization map on the bottom here, if this dimension inequality holds, it's a map from a small dimensional scheme to a large dimensional scheme. So it has to be non-dominant. And because it's non-dominant, that means you can choose some algebraic functional alpha on the codomain, which kind of vanishes on the image of the localization map. And so now what you want to do is you compose this functional alpha with your local Cohen map JP. This gives you some function f. So this f is a function on the QP points of X, and it takes values in QP. And by commutativity of this square, f vanishes on the set of rational points. And one can show that this function f is actually, it's analytic in the sense of Coleman. And yeah, because it vanishes on the set of rational points and only has finitely many zeros because it's analytic, this tells you that the set of rational points is finite. These functions f are usually called Chabauty functions. So just sort of summarize the whole theory I attempted to sketch in 10 minutes or so. Like the input in Chabauty theory is like a choice of a quotient of the fundamental group, and the output is a class of these functions called Chabauty functions. These are these analytic functions on the QP rational points, which vanish on the set of rational points. So that's how the method sort of works in very broad strokes and how it allows you to access finiteness results. But I kind of want to point out that at least as I've phrased it, these sorts of dimension inequalities between your local and global Selma schemes, these don't really have a hope of accessing any effective bound on the number of rational points. And the reason for that is that they tell you essentially nothing about these Chabauty functions f that you get out. They'll tell you that they exist and that they're non-zero, but it will tell you essentially nothing beyond that. And so there's really no hope with that little information of being able to say anything about the number of zeros of f, and hence anything about the number of rational points. So if one wants to make this all effective, then the thing that you need to do is to be able to understand better what these functions f that you are getting out of the method are. And to do that, I think there's kind of 3 steps you want to pursue in order to say anything about these functions f. So the first step is, I guess in my mind, the hardest step, which is we had this local and global Selma scheme and this map between them. And the first thing you need to do is to get some kind of handle on the geometry that's going on there. I've told you that these are two affine schemes of finite type and there's some algebraic map between them, but that really doesn't pin down the geometry well enough. So you need to say something more precise about the geometry of these Selma schemes. And then once you've done that, you should be able to convert this into saying something about what this Chabauty-Kim function looks like, so something about the shape of f. And then once you understand the shape of f, you want to translate this into a bound on the number of zeros of f, and hence the number of rational points. And I think it would be useful for me to illustrate what this actually means in practice when you carry it out for certain kinds of non-abelian Chabauty. So I'm going to start off with actually going back to this idea, this theory developed by Coleman. So Coleman's effective Chabauty theorem, so if you remember, we're assuming that the Mordell-Weight rank of the Jacobian is strictly less than G in this setup. And Coleman's aim was to sort of use Chabauty's method to bound the number of rational points. And I'm now going to extract that same bound for you. And we're going to do this by considering the following quotient of the fundamental group, namely its abelianization. And the abelianization of the fundamental group, sometimes denoted by U1. So if you remember these sets like XQP1 from Jen's talk, this is like all the stuff coming from the p-adic obstruction coming from this quotient U1. And another way of thinking about this abelianization of the fundamental group, by the way, is it's also the QP linear Tate module of the Jacobian. There, so there's very different ways of thinking of what this U1 is. But let's have a look at this Chabauty square in the particular case of U1. So when you follow through all the definitions, you try and work out what this global Selma scheme is. It turns out, modulo a small technical issue I don't want to really talk about, that this global Selma scheme is just QP tensor the Mordell-Weight group of the Jacobian. So it's an R-dimensional vector space. Or I guess if I'm going to be more precise, I should say it's the affine space associated to an R-dimensional vector space. So I want to take an R-dimensional vector space and view it as a variety in the obvious way. So that's what your your global Selma scheme is. Your local Selma scheme is something very similar, actually. It's the dual of the space of one forms on X, or equivalently, the dual of the space of one forms on the Jacobian. So again, that's a G-dimensional vector space over QP, and again, I want to think about that as a variety. And then this map along the bottom, what this turns out to be, so this is a map basically from the Mordell-Weight group of the Jacobian to the dual of the space of one forms. And it's the function which sends a degree 0 divisor D to the functional. Omega goes to integral of omega over D. I'm going to be a little bit, I'm not going to exactly spell out what this integral is, but like if your divisor D is supported very, very close to the origin, this is sort of the thing you would naturally expect it to mean. It's sort of, you formally integrate your omega and then evaluate it at the various different points of D. And then there's a procedure for extending this to all of your variety. So for the whole Mordell-Weight group. Sorry. But the sort of long story short here is that I've given you very precise descriptions of what these are, but if you squint, your global Selma scheme is an R-dimensional vector space. Your local Selma scheme is a G-dimensional vector space, and this map between them is a linear map. And what that information tells me is, well, if R is less than G, then this linear map between vector spaces It's certainly not surjective. And in fact, I can take a linear functional on the local Selma scheme, which annihilates the image. So I'm able to say something more precise than some algebraic functional. I can actually get a linear functional. And then when I pre-compose that with my local Como map, what that turns out to be saying is that this composition F here, this is actually given by integrating some fixed one form on my curve from the base point B to X. This is again integration in the sense of Coleman. So we've now kind of accomplished but the steps 1 and step 2 of that strategy I was describing earlier. We know that the Selma schemes are vector spaces and the map between them is linear. And then we've turned that into saying something about what this F is. It's in the integral of a one form. So the final thing to do is to use this information to bound the number of zeros of F. And this is an argument that Coleman came up with. So first of all, you can rescale. So we assume that our prime P is of good reduction in Coleman's setting. So we can assume that our one form that we've chosen is integral. So we can rescale it so that its reduction, so that it reduces onto the special fiber, and that its reduction is non-zero. And then if I have some point on the special fiber, well, the set of points which reduce to that, that's the residue disk of my point. And the number of zeros of this Coleman function F on that residue disk, it turns out to be at most 1 plus the vanishing order of omega, of the reduction of omega at that point on the special fiber. And so when you then sum this over all points, all FP points of the reduction, what you obtain is that the total number of zeros of this Coleman function F is bounded above by the number of FP points, which is the sum of 1 over all the points at FP points of X, plus 2G minus 2, which is the sum of those vanishing orders. So this is where Coleman's theorem comes from. You're bounded the number of rational points by the number of zeros of F, which we've just also bounded above. So that's where Coleman's theory comes from. And this result of Jenner and Netan's, as I mentioned for quadratic Chabauty, this also, you can also view this through a similar perspective. So let's briefly talk about that. So if you want to make your quadratic Chabauty effective, then we're going to use a slightly different quotient of the fundamental group. So let's take this rho to be the same quantity I described in words earlier. So it's the rational Picard number of the Jacobian. Then in this case, you can construct a quotient of the fundamental group, which is just slightly bigger than the abelianization U1. It's an extension of U1 by rho minus 1 copies of QP1. And quadratic Chabauty is basically about using the non-abelian Chabauty method for this quotient U. So what does our non-abelian Chabauty square look like in this quadratic Chabauty setting? Well, it turns out that passing from this quotient U1 to this larger quotient U turns out not to change anything on the side of the global Selma scheme. Okay, and there's another second issue I'm now sweeping under the rug. So apologies if you know what that issue is. Yeah, so the global Selma scheme hasn't changed. It's still an R-dimensional vector space. But your local Selma scheme has changed. And in fact, it doesn't really naturally have a vector space structure anymore, but it is at least an affine space. And it's an affine space of dimension G plus rho minus 1. And then this localization map between them, it's a map, it's an algebraic map from an R-dimensional vector space to QP to the G plus rho minus 1. It turns out that with a nice choice of coordinates, the first G coordinates of the localization map are all linear, and the next rho minus 1 coordinates are actually just quadratic functions on the Mordell-Weil group. There are quadratic functions which are, when you actually unpack all of this, they're related to global height pairings. That's going to be not really, I'm going to suppress that viewpoint mostly here. And then the final thing I'll describe on this diagram here is this non-abelian Cohen map JP going from the QP points to your local Selma scheme, which is this G plus rho minus 1 dimensional space. And it turns out that what this map here is, in terms of these coordinates, the first G coordinates of this map are given by single Coleman integrals. So the same thing we saw in the for the quotient U1. But the next rho minus 1 coordinates of this map are actually slightly more exotic functions. They are double Coleman integrals. And they are specifically double Coleman integrals which are related to local p-adic heights. But for today, we're just going to think of them as some kinds of double Coleman integrals. We're seeing iterated integration enter the picture. So this is a precise description of what this square looks like in the setting of quadratic Chabauty. So the next thing I want to do is to try and use this information to say something about this Chabauty-Kim function f that came out. And I'm going to make some slightly simplifying assumptions, which I've just written on the left-hand side of the slide. So in particular, I'm going to assume that the Mordell-Weil rank of the Jacobian is equal to the genus. I'm going to make a slightly stronger assumption than that. But in this context, what that's saying is that, in this bottom arrow across the bottom of this square, it's saying that the first G coordinates of that map actually give you a linear isomorphism between the global Selma scheme and Q to the G, so the first G coordinates. If you think about what that means is that the image of this localization map is going to be the graph of a function from QP to the G to QP to the rho minus 1. And in fact, it's going to be the graph of a quadratic function. And what that means is that for this alpha I'm going to choose, this algebraic functional, I can choose something like, I can take my G plus ith coordinate for some I and subtract off the corresponding quadratic function in the first G coordinates. And that will be some functional which vanishes on the image of the localization map. And then when I transfer this over to the function f, which I get by pulling back along JP, it turns out to say that my Chabauty-Kim function, this is just given by some double Coleman integral, which I've written here as a p-adic height, but whatever this function is, this is a double Coleman integral minus some quadratic function in some single Coleman integrals. So now we understand in this quadratic Chabauty setup, the shape of these Chabauty-Kim functions quite well. But we now need to try and use this to bound the number of zeros of this function f. And we're going to have to do this using a new idea which Jen and Netta introduced. So we can't actually use the same idea as Coleman did. And instead, we're going to try and bound the number of zeros of this function by writing down a differential equation which it satisfies. And so this is their idea. So we're going to let's take t to be a non-constant rational function on x. So like dt is rationally speaking a generator of the one forms on x. And we're going to be working in the sort of ring of algebraic differential operators. So that's sort of the ring, the non-commutative ring generated by the rational functions on x and d by dt. And what you can do is you can find you can always find a differential operator which kills any finite number of rational functions you like. And so we're in particular going to take, so omega 1 up to omega g is going to be like a basis of the one forms on X. And then we want to take a differential operator which kills omega j over dt for all j. So that's g different rational functions. And what Jonathan showed is that if you take this function f, which is some very like analytic function, if I differentiate f with respect to t and then hit it with this differential operator d1, the result of that is not any old analytic function. It's actually a rational function on the curve. And so this is really giving you like a differential equation which is satisfied by my analytic function f. And what they show is that if you are very careful about how you choose this d1, then you can actually use this differential equation to say something about the Newton polygon of your analytic function f, and then therefore say something about its number of zeros. And that ultimately is what gives them their bound on the number of rational points. So having talked through those two particular examples of abelian Chabauty and quadratic Chabauty, what I want to talk about in the remainder of my talk is what goes on beyond that. If you choose sort of the wild west of the general non-abelian Chabauty method, so we're going to take a general quotient of the fundamental group, and I want to see what I can say, for each of those three steps of that strategy I was describing earlier. And the main thing we need to do to understand the geometry of the global and local Selmer schemes is somehow motivated by this idea of thinking about weight filtrations on varieties or anything else which crops up. So, so this quotient of the fundamental group, however I've constructed it, it comes actually with a canonical filtration on its affine ring, which is called the weight filtration. And this filtration is basically the one which is induced by the descending central series on my group U. And when you follow through the constructions of the global and local Selmer schemes, whatever they are, this weight filtration induces corresponding filtrations on the affine rings of my global and local Selmer schemes. So yeah, these are not just any old affine schemes. They're affine schemes with a filtration on their coordinate rings. And then this localization map that we had from the global Selmer scheme to the local Selmer scheme, this actually is a filtration preserving map on the level of their affine rings. So this may not be very obvious here from the way I phrase this in a very sort of algebraic manner, but this does actually tell you something about the geometry of the local and global Selmer schemes and the map between them. I think this is easiest to illustrate in an example. So let's suppose we're in this nice abelian setup. So we're taking the abelianization of the fundamental group. Then, I said that the global and local Selmer schemes, these are just QP vector spaces, where I pretend that those QP vector spaces are varieties in the usual way. And what that's really saying is that the affine ring of the global Selmer scheme is just the symmetric algebra in QP tends to the Mordell-Weil group dualized. And something similar for the local Selmer scheme. And I've just promised you that the rings on the left-hand side of these equalities come with some canonical filtration induced from the descending central series on U1. And it turns out that filtration is just the usual filtration you get on symmetric algebras. So basically the filtration by tensor length. And so that says something a little about the geometry of these two things, but crucially, it really says something strong about this localization map. So this localization map which a priori, is in full generality is just some kind of polynomial map between these two things. The fact that it preserves these filtrations on the affine rings, that means that this, when I write it out in coordinates, the localization map is like affine in each coordinate. So it's degree at most 1 in each coordinate. And so the moral of this example is that the existence of these wave filtrations and the fact that the localization map is compatible with wave filtrations, this is almost already enough to capture the fact that in the abelian case, everything is a vector space, and the map between them is linear. So this actually is saying something concrete about the geometry of the localization map. So with that, I now understand enough about the geometry of the Selma schemes and the Chabauty-Kim diagram. So the next thing I need to do is to understand something about this localization map. And so what I'm going to be saying is now very, very general. But the slogan here is that this localization map is, sorry, not the localization map, the non-abelian Cohen map from QP points to the local Selma scheme. This is given by Coleman integration. So I'm going to be a bit precise about what this means. And if you're going to do this in full generality, I think it's most convenient to take the perspective on this, which was developed by Amnon Besser. So very slightly modifying his definition, we're going to define an abstract Coleman function on my curve X to be a triple consisting of 3 things. First of all, a unipotent vector bundle with integrable connection on my curve. And I'm also going to choose a point in the fiber of that vector bundle over the base point. And I'm also going to choose like an OX linear map from my vector bundle to OX. So not requiring any compatibility with filtrations. And the set of all abstract Coleman functions, there's a natural equivalence relation on this, which is something to do with morphisms of vector bundles. And if you mod out by that equivalence relation, then the set of all abstract Coleman functions end up forming a ring, which is called the ring of Coleman functions on X. It's noted O col of X. So this is quite a nice way of handling Coleman functions, certainly from a very sort of abstract point of view. One thing that is very much missing from this description right now is why on earth it's legitimate to call these things functions. Because a function should take an input and give you an output, and I haven't really explained how to evaluate a Coleman function in this sense at a point. So let's briefly talk about that. So if you give me if I take any QP point on my curve, it turns out this is some quite amazing theorem proved by Coleman, and I should, I guess, re-emphasize at this point that I'm talking about varieties with good reduction at P. So if I have any vector bundle, any unipotent vector bundle with integrable connection on X, then I can look at the fiber over B and the fiber over X, and there's a canonical way to somehow use the Frobenius on the rigid fundamental group to identify the fiber at B with the fiber at X. So they're isomorphic. The isomorphism between them is sometimes called parallel transport along Frobenius. The name here is warranted because if I choose X really, really close to B, this parallel transport is parallel transport along Frobenius. This is just the thing you get by integrating up the connection. But this somehow the miracle is you can pass even between different residue disks in this theory. And so this gives us a recipe for evaluating Coleman functions. So if I take an abstract Coleman function, and I take my point X and I want to evaluate it, the way I do that is I start from this point, this element V, which is a point in the fiber over the base point B. I then parallel transport that over to a point in the fiber over X. And then if I apply my functional Tor, that gives me a point in the fiber of OX at my point X, and the fiber of the structure sheaf is just QP. So this is giving me a genuine element of QP attached to my point X. And this is how we view abstract Coleman functions as bona fide functions on X. So okay, I won't talk about in the interest of time, I'm not going to say too much about this, but just to give you one example, if you take a one form, you can cook up from that one form a unipotent vector bundle with connection by taking the like a trivial rank 2 vector bundle, but you give it a slightly twisted connection involving omega. And when you construct this abstract Coleman function, you end up with the function you define. It's an analytic function, and it has the property that its derivative is omega. So it's an anti-derivative of omega. And it's a sort of canonically chosen one as well, which is very surprising. And so this function is called the Coleman integral of omega. So that's, if you've seen Coleman integrals before, that's how Coleman integrals fit into this formalism of Coleman functions. And one thing you can observe here is that this ring of all Coleman functions on X is actually a natural filtration on that, which is I can look at the subspace consisting of all Coleman functions where this vector bundle with connection is unipotent of class at most n, and that will give me some subspace of the ring of Coleman functions. And what you can show, I guess, is that, yeah, so I asserted earlier that this local Cohen map JP is given by Coleman integration. And the precise statement here is that if I fix my quotient of the fundamental group U, I get a corresponding subring of the ring of Coleman functions with two properties. First of all, this local Selma scheme I want to understand is actually just the spectrum of this subring of Coleman functions. And this identification here, by the way, is compatible with the weight filtrations on their affine rings. And then secondly, this local Cohen map from the QP points of X to the local Selma scheme, i.e. to spectrum of this ring of Coleman functions, this just sends a point to the evaluation at X functional. So this is So the map JP is given by Coleman functions. And one kind of key aspect of this theory is that you can take this differential operators argument that Jenna Netan developed. You can do a sort of iterated version of it. And when you iterate this construction, you can actually bound the number of zeros of a Coleman function in terms of its weight. So yeah, if I have a non-zero Coleman function of weight m, then the number of zeros is bound on each residue disk is bounded above by this quantity here, which depends on the genus, depends on the weight m, and this kappa p is some constant depending on p only. So if you when you kind of feed this into the combine all of these ideas, you end up showing the following theorem. So suppose that the dimension of the mth weight filtered piece of the affine ring of the fundament of the global Selma scheme is strictly less than the dimension of the mth weight filtered piece of the affine ring of the local Selma scheme. So, if you have this, then you obtain an upper bound on the number of rational points in terms of this constant kappa p, the number of fp points on X, and then some function which depends on just G and the weight m. And I will just very, very kind of quickly sketch how this goes. So what we've seen so far is that for this in the full generality, this non-abelian Chabauty square, we know that the lower left and lower right corners, these are affine schemes with a filtration on their affine rings. We know that the map between them preserves that filtration, and the right-hand vertical map is just evaluation of Coleman functions. And the key point here is that if I look at the pullback along the localization map on the weight of most M parts of the affine rings, well, this is a map. This is a linear map from a large dimensional vector space to a small dimensional vector space. So it has non-trivial kernel. And so that an element of that non-trivial element of that kernel, that is a functional alpha we're looking for. So when we try and use this to produce a Chabauty-Kim function, the alpha has weight at most M, and therefore the Chabauty-Kim function is a non-zero Coleman function of weight at most M, and so we know how to bound its number of zeros. And so that's how you prove this result. And I think I just want to very quickly at the end illustrate some kind of more concrete consequences of all of this theory. So the first thing is the formula I've written depends on this and this weight M. Can you estimate this M or anything like that? And so if you assume somehow the usual conjectures on kind of coming from the theory of motives, you can actually predict what weight M should hold, the previous inequality should hold for, and you in fact end up with an explicit upper bound on the number of rational points on your curve. Of course, this is like nowhere near as good as Dimitrov-Gauss-Haberger, because this result is it's conditional. It depends on more things than just the genus and the rank. But it does have the rather interesting aspect that this is completely explicit. Like here is the formula. I haven't told you what NL is. You can ask me later if you want to know. So this method is really giving us completely explicit bounds on the number of rational points. And then you can also apply this to the S-unit equation. And the thing you get for the S-unit equation, again, this isn't as strong as Evertz's bound, but it is completely explicit, depends just on the size of S, as one would expect. And so I think where this theory is at the moment is that we can produce bounds on the rational points using non-abelian Chabauty. We still aren't quite up to the stage where we can exactly compete with things coming from Diophantine approximation, but I think I think it's very interesting to think about, maybe very speculatively, whether you can combine these different techniques, Diophantine approximation and non-abelian Chabauty. I think I'm already a little over time, so I will stop there, and if anyone has any questions, I would be very glad to take them.
Thanks, Alex. That was a wonderful talk. Great. Well, let's see. Would anyone like to ask some questions? Well, maybe I'll start with one. For the upper bound with the S-unit equation, is that something you could test to see like whether you ever realize that bound?
Yeah, so I guess the one thing is that this bound that I've given is like doubly exponential in the size of S, and Evertz's bound is singly exponential. So I guess this bound here is never going to be sharp, because it's just we know a better bound. As for Evertz's bound, I believe Erdős and a couple of other people gave some lower bounds on the number of solutions to the S-unit equation, or like they chose S suitably and showed that you could get, I think, faster than polynomial growth. So this exponential seems sort of the right order of magnitude. But I think maybe more broadly, with the exception of Coleman's bounds, all of these other bounds that we're seeing are probably vastly too big. I mean, for example, they're doubly exponential rather than singly exponential in some quantity. So yeah, the question of using this to obtain possibly sharp bounds is also a very intriguing one, but I don't know how to say very much about.
Well, thank you. Would anyone else like to ask a question?
I had a question. How do you choose your number m, like the weight m?
Hmm.
So given a u, how are you choosing m? Is it like the same as the depth of u, or like can you do better? Because like your bound grew as m grew.
Yes, absolutely. So yeah, where does this m come from in practice? So yeah, if you choose u to be like the depth n quotient, I don't actually well, okay, I guess from my work with David and Marius, you can predict what the value of m should be for that, but it's going to be something complicated. But really, the way that I would approach this is this function on the left-hand side. So the dimension of the weight at most m part of this ring, and this is really controlled by like the Hilbert series associated to that filtration on that ring. And you can exactly compute that Hilbert series, like assuming you know like the dimensions of the certain Bloch-Carté-Selmer groups. And so you can write down this Hilbert series, you can write down the corresponding local Hilbert series, and you can just compute them out to a very large value of m and see where one overtakes the other. That's where the computations come from.
Yeah, thanks.